Okay, I'm going to go ahead and apologize now. My cats are acting psycho tonight. They're running around and meowing and being crazy, so I apologize if I have to stop this at any point to scream at them. We had kind of touched on the topic of differentiability a little bit in section 3.1. We said a function is differentiable, meaning it has a derivative as long as the slopes of the secant lines has a limit. Okay, that was IROC. So when will it fail to have a derivative? Well, a function is going to fail at one of the 4 points that we're going to talk about. The slopes of the secant lines are going to fail to have a limit, meaning the left-hand side derivative and the right-hand side derivative will not be the same. Okay, so for example, if you've got a corner, okay, we looked at the absolute value graph before. The left-hand slope and the right-hand slope are different, and there's not a smooth transition between the two of them. So at this location, let me get a different color here. At this location right there, right at the vertex, this is going to fail to have a derivative. Okay, the second point that we can talk about as far as failing to have a derivative would be at a place like a cusp. And a cusp, I always consider it like a little seagull shape. And the slopes are approaching infinity and negative infinity from the left and from the right hand side of that location. So at this, again, it's kind of like a vertex right here. All right. From the left hand side, the slopes are approaching negative infinity. Okay. This function is decreasing and it's becoming a steeper and steeper negative slope. But just to the right hand side of that vertex, it's a very, very positive slope. So from the left and from the right, they fail to meet the same number. Okay. A vertical tangent is a location where the slopes would either approach positive or negative infinity, and these never work out when I try to draw them. But a perfect example, I guess we'll use red this time. Perfect example comes from the cubed root graph. At the location right where it kind of goes vertical, right there. All right, this will fail to have a slope because technically the tangent lines, let me get a narrower pen here. The tangent lines are slightly positive, more positive, more positive, more positive, and right as you get to that point, it becomes a vertical tangent. And like I said, it's really hard to draw, so it looks accurate, but I'll show you an example in class. And then just to the right of it, they flatten back out. But at that one location, that vertical tangent, the slopes are approaching either positive or negative infinity. In this case, positive infinity. Okay, so if you think back to what a slope of a vertical line is, it's undefined. So if a slope is undefined, that means the derivative is undefined as well, because slope and derivative mean the same thing. A discontinuity, meaning the one-sided derivative does not exist. Any kind of discontinuity would work, so let's go ahead and just, I don't know, put something like this. Okay, for a location such as this right here. Okay, from one side the slope is one thing, from the other side the slope is another, and we're going to show some problems in class which proves that the one-sided derivative will not exist on both of these guys. But so that's it, the 4 locations there. If your graph has any of those, the graph can have a derivative everywhere else, but just not at those locations. Okay, for this next part, example 1, this is actually on your own. And if any of you have difficulty doing this, we'll talk about it in class tomorrow and we'll show it. But this is discovering local linearity. If you graph f of x equals x squared on your calculator, I want you to continue zooming in at the location of 0, 0. And then I want you to make an observation about what happens as you zoom in. After you've done that and you write down your observations, I want you to do a new graph and repeat the process for the absolute value of x. And this time, same thing, zoom in repeatedly, at least 5-6 times. And again, make another observation. Okay, then once you're done with those 2 things, I want you to go ahead and predict what local linearity is. Okay, this is what we're going to start class off with tomorrow, so you got to have something written down for this. So a function will be differentiable where it is locally linear. In order for a function to be differentiable, it also has to be continuous. However, the converse of that isn't always true. If a function is continuous at a point, it doesn't mean it's differentiable at that point. So we're going to take a look at 4 graphs right now, and the first one is going to be differentiable and continuous at x equals 2. So that could be any function as long as it does not have a vertical tangent, a cusp, or a corner at x equals 2. But at this location, there's no jumps, there's no holes, there's no gaps, and it is a smooth function in the sense that the derivative from the left would equal the derivative from the right. For graph B, we're trying to draw a graph that is continuous but not differentiable at x equals 2. So again, this graph could have a corner, a cusp, anything, a vertical tangent, as long as it's continuous. But again, this is one of those situations that we talked about on the previous page where the left-hand derivative would not equal the right-hand derivative. But obviously, it's continuous. You could draw it without picking up your pencil. For graph C, not differentiable, also not continuous at x equals 2. Well, based off of the fact that it's not continuous, you could have, wow, that was really pretty. You could draw a piecewise function or anything vertical asymptote as long as it's not continuous at x equals 2. And then D, to draw a graph that's differentiable but not continuous, this is not possible. It has to be continuous in order to be differentiable. Alright, so we're going to start dealing more with the calculator, especially with the new calculators. It's going to be really important that we go over it in class, but your calculator can't do limits. So essentially what it does is it uses AROC, which is, this is technically called the difference quotient. We didn't call it that before, but it's the difference between two things and it's a quotient. That's why it's called that. This should look familiar. This is the slope between 2 points, and then this was AROC, and we made it turn into an instantaneous rate of change by taking the limit as h approaches 0. Now, this next guy, this symmetric difference quotient, it's not much difference, but let me point out what we did with AROC. We had a point A, we moved over an amount h, so this would become A plus h. So we were technically trying to find the slope between these two guys. Now, to make that a tangent slope at A, again, we took the limit as h approaches 0. So this point would be moving closer. The symmetric difference quotient is exactly what it sounds like. If your point is A and you've got a curve and you're technically trying to find the slope at that point, you'd move over an amount A minus h and you'd move over an amount A plus h, and that's going to be much more accurate to the tangent at A than just using A and a point to one side of it. It narrows it out. So we're going to talk about how does the calculator do this. Well, when we do the limit as h approaches 0, we're going to use the symmetric difference quotient on this one. Again, it's just another way of finding slope between 2 points, but as soon as you put in that limit piece, okay, and then difference, by the way, the difference would be 2h because if you started at a point A and you move over h, right, move over this amount h, and then there's the amount h over here on this side, so you're ending up with an x difference of 2 h's. But again, so this whole piece in here, this is finding slope between 2 points. As soon as you put in that limit as h approaches 0, now you're finding the tangent. Okay, you are approximating the derivative. Because your calculator can't do limits, what it does is it says instead of doing the limit as h approaches 0, it's just going to use h with a value of 0.001, which is so close to taking a limit as h approaches 0 that it's a pretty good approximation. So this is how your calculator actually finds the derivative if you give it an x value, and we'll talk about this in class more. Alright, we're going to look at example 3 now. It says use the symmetric difference quotient to find an approximation for the numerical derivative of f of x equals x cubed at x equals 2. So I've even said here, don't use a limit as h approaches 0, just use the fact that h can equal 0.001. So again, it's an approximation, it's not an exact derivative. So if you use the symmetric difference quotient, we're going to do f of a plus h minus f of a minus h, all divided by 2h. Now we're going to plug in our knowns. Our a value at this point, remember I said anytime you see at, that's telling you the a value. So this is going to be f of 2 plus h, but I already said h is going to be 0.001. And then we're going to do minus f of 2 minus 0.001. And again, that's just function notation. We'll be able to simplify all this in just a second. So we're technically trying to find f of 2.001 and f of 1.999, all divided by 0.002. Okay, if you do 2.001 and you cube it, and then you do f of 1.999, which means take the 1.999 and you cube that. Do all that on your calculator, and you'll come up with an answer. And you should get 12.000001. Which obviously, if you round that to 3 decimal places, which we always do, you're getting a value of 12. For this next one, we're going to graph f of x equals the absolute value of x minus 1, and then we're going to use our calculator to find the numeric derivative dy dx at x equals 1. So I want you to go ahead and do this on your calculator and then answer the question, does your answer make sense? Why or why not? So again, this is going to be something that I'll be checking tomorrow. All right, have a good night.